I'd like to first thank the LSSW organizers for this opportunity to talk about my research. My name is Vidwans. I'm a postdoc at WashU in St. Louis, and I'm working under the advisement of Dr. Jeffrey Gillis-Davis, who leads the survey node here at WashU called ICE50. And I'd also like to acknowledge the McDonald Center for Space Sciences at WashU for partial funding for this project. So today I'll be talking about an instrumentation concept, essentially using air quality sensors that are common here on Earth to try and monitor the spatiotemporal distribution of dust on the moon resulting from PSI activity. Next slide, please. So as you all have heard in great detail, PSI events have a large effect on the lunar surface, including volatiles and dust, in a way that we don't fully understand yet. Now, when thinking about in the focus of dust, as an instrumentalist in terms of measuring dust, I think about the velocity of the dust. And for those of you who are familiar with dust measurements done in space, you know that impact ionization is a very popular method to measure dust. This involves striking the dust particle against a surface where it turns into a plasma, and then you can use a charge-sensitive amplifier to measure the plasma coming off the dust, which you can then infer its size and charge. The problem with this technique is you cannot use this to measure low-velocity dust. And while a lot of the dust particles displaced by plumes are high velocity, there's also a lot of low velocity dust that settles down onto areas far from the landing site at longer times from when the landing or ascent occurs. Now, it's important to understand the size distribution of these dust particles because it has significant effects on, firstly, the extent of the hazard that the dust particles are posing, and also how to mitigate the risks caused by the particles. So when you think about particles depositing onto a surface, what mitigation strategy can you use to remove them from the surface, and how effective will that strategy be? It depends on the particle size distribution. So what I'll talk about here is using a network of sensors, optical sensors, that are very low swap that can be distributed all over the surface to try and measure the particle size distribution in real time. So firstly, we can have some concrete ground truth type data to compare to our the robust models that have been talked about during this conference. And also on a broader level, try and establish the protocol or policy for how far away these landers should be from nearby lunar activities. As more and more countries start sending landers to the moon to conduct scientific or resource-based activities. Next slide, please. So during my grad school work, I did a lot of work on tech transfer between air quality here on Earth and the tech development that has been done here for measuring pollution and transferring that to monitoring dust in the lunar environment. So we're very interested in measuring air quality here on Earth, especially in the last 10, 20 years as technology has become miniaturized. There's lots of pollution here on Earth, as we know, and in certain countries, the regulations are not as strict as they are in the States, and people unknowingly get exposed to poor air quality. Now, these miniature particulate matter sensors are very useful for helping inform the public on the safe breathing conditions for air and understanding how much particulate matter is in the air. So an example of one type of these sensors is in the bottom left-hand corner here. It's called the Sharp GP2Y sensor. It's what's called an ensemble scattering sensor, also known as a nephelometer or a photometer. It's extremely simple. It has an infrared light source that illuminates particles that move through the sensor through this through hole. The particles can be driven by airflow, but also in the case of a vacuum environment, they can be driven by ballistic motion or being moved by a plume. The aerosol interacts with the light and scatters it in all directions as a function of its size, shape, and composition. And there's a light detector located to the left that converts the photons to a voltage signal. And you can perform calibration experiments in the lab to see how the sensor output corresponds with mass concentration. And this is what we did in this paper that came out earlier this year for my thesis. We used this sensor, exposed it to two different lunar dust aerosols, aerosolized in two different ways, so 4 unique aerosols, and we looked at how this proportionality between the sensor output and our reference concentration changes. Then we took it a step further and put the sensor in a vacuum chamber to prove that it can operate under vacuum conditions also. And we mobilized dust inside our chamber using sort of like a plume, an air jet that we injected into the chamber to mobilize a container of dust. And we saw pretty strong correlations there as well. Next slide, please. So the problem with these types of sensors is you need to know the particle size distribution beforehand in order to get an accurate measurement. And this is because there's only one input and one output that you're getting from the sensor. So in this equation on the top right here, you have this calibration factor K that describes the proportionality between your sensor output and the mass concentration. And this factor changes wildly depending on your particle size distribution, even if you're holding the type of simulant constant. So the solution to this, when thinking about the lunar environment and our inability to know a priori this particle size distribution, is to use a polychromatic setup, where we have the same geometry, but instead of a single wavelength light source, we have a polychromatic source, where we have basically white light that you're exposing to the aerosol. And instead of a single wavelength detector, you have a spectrometer, so you can get a spectrum as the output rather than one single analog output. And this allows us to have a wealth of data instead of one single data point, where we can put it into an algorithm and try and back out the entire size distribution parameters. So basically 3 parameters that would constrain the size distribution function. And we would do this by solving a system of integral equations you can see on the bottom right. In essence, this equation, it adds up the individual, the light scattered by each individual particle in your size distribution, and sums it all up at each wavelength. Now, while this seems relatively simple, this function I of dp lambda inside that equation is highly complex, and I'm happy to see a lot of discussions here in this conference about light scattering and optical behavior of lunar dust particles. And as we know, it's a very complex process because of the irregular size and shape and composition of lunar dust particles. So this highlights the need for progress in light scattering models as well as laboratory experiments. Next slide, please. So to kind of demonstrate as a proof of concept for this polychromatic nephelometer type instrument, we did a very basic experiment where we put a optic fiber in a chamber, pointed at a beam of white light coming from outside the chamber, and we injected into the chamber different types of aerosols. And we monitored the scattered light spectrum coming off the aerosols, and kind of on one level, just looking to see that this scattered light spectrum is different than the incident light spectrum. And then secondly, see if we can discern between the different types of aerosols that we were injecting in the chamber based on the scattered light spectra. So you can see on the bottom left-hand side, we have a few different spectra plotted here. The dotted line is the incident white light that the aerosol was exposed to, and then the other solid lines are the scattered light spectra from the different aerosols. So we can see that these lines break off into different areas, showing that they are scattering light differently and exhibiting different optical behavior. And on the bottom right side, we calculated intensity ratios. So our light intensity from the scattered spectra at different ratios in these spectra. And we can see that certain ratios show the fingerprint, so to speak, of the aerosol versus others that are relatively simple. And this kind of exercise helps us inform what spectral range should we be looking at for a next generation instrument that shows more of the fingerprint of the aerosol, gives us more information about the aerosol. Next slide, please. So in conclusion, what I've talked about here is the concept of using a instrument inspired by air quality monitors on Earth to try and establish a network of sensors on the moon that we can use to understand on a fine resolution scale how dust moves around, and helps us measure the size distribution so we can understand the hazards and what mitigation strategies to use. What would be involved in developing such a sensor would be both on the theoretical and experimental side. We need to make progress in understanding light scattering behavior of these particles to help us back out size distribution parameters from this light scattering instrument. We would also need to carefully select which miniature spectrometer we want to use. There's lots of different kinds out there. Some are grating based, some are photodiode array based, and also which light source do we want to choose that kind of balances having low swap, but also giving a high enough intensity so we can measure those smaller particles. And then finally, doing realistic environmental testing in a dust bin is also crucial to development of this instrument. I think that's the last slide I had. So thanks for listening, and I'll take any questions in the chat later. Thank you.